Hello everybody, my name is Jonathan Radomski. I'll be presenting today for my Bachelor's of Science in Applied Science and Technology in Nuclear Energy Engineering Technologies as part of Thomas Edison State University. For the capstone course rather, NUC-495, I will be presenting on developments in computer simulation and the effect on the nuclear power industry. It's a paper that was written by Jeff Gannon, Jonathan Isaac, myself, and Justin Schneid. I'd like to most specifically today cover a bit of the history of simulation, actually the majority of the requirements federally and industry accepted practices for simulation devices, as well as some of the impacts that simulators have had on the industry. First thing I'd like to discuss, however, is what a loss of coolant accident is. It is a postulated accident that results in the loss of a reactor coolant at a rate in excess of the capability of the reactor makeup system from breaks in the reactor coolant pressure boundary up to and including a break equivalent in size to the double-ended rupture of the largest pipe in the reactor coolant system. The reason I discuss this is there's three major incidents in the history of nuclear power that most people are familiar with, and that's 3 Mile Island, Chernobyl, and most recently, Fukushima. These incidents occurred and were worsened by the fact that operators took incorrect actions, 3 Mile Island being the worst of the three. However, all had significant operator contributions. A little history on simulation. In the early 1950s, simulation was developed along with the earliest nuclear power plants. Initially, it was just devices that were operated by computers that were fed pre-recorded simulated operations. So, for example, a reactor operator could sit in front of a panel that they would be operating on the plant that which they were training on, and the actual operations would occur on the panel in front of them, lights, indications, etc. Any changes in any of their pumps or etc. Could actually be played out as if they were performing the operation themselves. However, there was no interaction with it. It was, like I said, a pure replay model. This continued with some development up through 1979, but the 3 Mile Island incident occurred, and this definitely spurred the industry. They realized at this point that a major loss of coolant accident could be mitigated if the operators had the proper training. So they decided to start focusing on what would be necessary to get the simulation technology up to the point at which they could actually train the operators on a loss of coolant accident. Throughout the 1980s, continued to develop. It wasn't until the early 1990s that the NRC started really accepting the use of simulation in training of future operators or for continued training of operators. This, a lot of ways, was done because throughout the 80s, the development was completed for simulators in a manner that forced them to have better core models than industry practice was for development of new plants. So there was actual three-dimensional core neutron flux that was required to be calculated out for the simulation devices, but that third-dimensional aspect of it wasn't required necessarily for development of new core models for just regular commercial use. A nuclear simulation facility, according to the NRC, is one that is prototypic of the plant that the operator will be training on. What I mean by that is it's representative of the equipment that they will see when they are training. The commission must approve that simulator, and it must include items that the operator will be training on. For example, it must have components that would be specific to training on a certain task, maybe certain valves or other such components. Or most commonly, it's going to be something more like a control room simulator, which is going to be an entire full-scale mock-up. In order to certify a simulator, there's a lot of requirements that the NRC requires that be met. Most importantly, actually, is visual fidelity. It must react and look as if it were the actual plant. It must be prototypic of the plant that the operators themselves are going to certify on. It must model the actual nuclear and thermal hydraulic characteristics of the plant. So in other words, as heat is added, you see the associated temperature rise and cooling effects and yada yada yada. But most importantly, and the one that is often most difficult, is it must remain prototypic of the plant. So if there's some sort of field change that is installed on the plant, this must be also reflected in the simulator itself, which does provide for training operators on new equipment as it's being developed, but it also means that they're training on the most prototypic device. Some of the requirements are bound by 10 CFR 55. Again, in section or part 46, they discuss actually what is a simulation facility. And like I said, it must include a reference plant that is prototypic, it must be approved, and it must maintain most up-to-date configuration. Another part of it is that there's a minimum number of practical knowledge factors and operations that must be completed. On this list, you'll see things. For example, this list is 10 CFR 45, sorry. And that list actually includes items that can either be performed on the plant or can be discussed with an operator. On this are going to be things that are items such as heat up or cool down of a plant, or discussion items include things like emergency operations, radiological emergency drills, any sort of actual plant emergency that would require an overall operational knowledge of the plant. But then there's also the second list that is part of, actually it's listed in the requalification section of 10 CFR. It's part 50 or 10 CFR 55. This is part 59. But this actually has a list of A through all the way through Z and then AA of different evolutions that the operator must perform while going through training, and this is going to include things that require them to perform dynamic plant operations. This might include something like a plant startup, or plant shutdown, or heat up from a cold iron situation. There's also casualties included on this, such as a loss of coolant or a loss of vacuum casualty, a rod out of alignment. All of these items are going to be things that they have to, of these items, they're going to have to pick, the staff will pick 5 that the trainee must perform throughout their qualifications as part of their final certification testing. I'd like to discuss the ANS, who has been the most vital component of developing the standards by which the federal government operates. As early as the TMI incident, the American Nuclear Society recognized the need for standards in the simulation community. The American Nuclear Society is a nonprofit professional organization that, contrary to the American part of the name, operates on an international basis. And they work to further understanding awareness in nuclear science and technology. And so they actually do develop industry standard practices and expectations. Among these, they developed what's known as ANS 3.5. it defines the requirements as the industry saw fit, and this has actually been revised multiple times since 1979 to stay current with training standards today in plant operations as they are now performed. They require some specific functionalities of the simulator that we have not yet talked about, and a couple I'd like to cover are actually freeze, speed adjustment, replay, or the ability to insert malfunctions as we refer to them. First off, we'll discuss freeze, which is the ability for the staff instructor to be able to stop the simulation at any given time. This is a beneficial tool that will allow the staff to potentially take a break and discuss an item with an operator. For example, they're getting ready to begin a complex evolution. They can freeze the simulation and say, okay, what are we going to perform next? What do we expect the indications to be? And how are you going to respond to those indications? And then immediately resume exactly where the simulation had stopped before. Or if an operator is making a mistake, they can freeze it and help them discuss their way out of it. Next is the ability to adjust the speed at which the simulation operates. This is not necessarily used as a training tool, to be clear. This tends to be something that's used more for certification and testing. What this does is this allows the trainer to be sped up or slowed down. You could speed it up, for example, to get through a complex evolution. So if you're a good example of this is if you're performing a cooldown and you have to maintain a certain cooldown rate, what you can do is set a cooldown rate but change the overall time speed of everything. In other words, you're still actually going to have the same cooldown rate, but a minute will pass faster than a minute and not allow you to perform the operations without violating any limits. Or you can actually slow something down. This is good for trying to figure out what happened in a situation. For example, if there was an error in the simulation, or if a student kind of reached in and did a lot of operations all at once, the staff can then go back, or the test engineer can then go back and slow things down and see what happened. Or they can do it in real time and actually slow it down to see, like, okay, if I isolate vacuum right now, how quickly are things going to start falling apart? The next is replay. Replay is an excellent tool for both testing and training. Testing, of course, it's great for if you find an error, you can bring that error back and have it reperformed to help the software development community correct it. Whereas in the training community, it's a very powerful tool because it allows the staff to actually rewind and go through a training set again. So if you had a full engine or a full reactor plant team in the control room, and each had their own staff instructor and they were performing evolutions rapidly, there might be subtleties that are missed. What this will then allow them to do is to go back afterwards, watch it all together and say, well, at this point this happened, and you maybe should have shimmed in here or done some other operation which could have controlled power. So that actually provides a dual purpose. The last is the ability to insert or remove malfunctions. And this is vital to actually achieve the certification. This is basic functionality of the simulator. What it does is it allows the instructor to insert some sort of abnormal situation, something like, for example, a turbine bad bearing, or a loss of coolant accident, or even loss of vacuum, etc. Any of these allowing the staff to insert an anomaly on the student and forcing them to react and figure out their correct operations. This has actually been hugely accepted by the industry. The savings of these simulation devices has been astronomical. They say that an outage can cost as much as $1 million per day, um, and simulators can save that amount of money. And the fact that it allows new staff for the facility to be trained while there are other operations going on. I mean, you can't necessarily train a staff to shut down a reactor if you don't have a reactor shutdown scheduled for another 3 months. So instead, what this allows you to do is to walk through the operation with a student trainee, certifying that operator in advance of that actually occurring. It also is good for new plant development because as a new reactor plant is developed, for example, most recently, the one that we're familiar with in America is Westinghouse's AP1000 plant. When that was deployed, and even actually before construction began, there was a simulator that was built with the first person or the first principle characteristics that allowed them to not only test items before it was actually built, but also allowed them to train the operators so that as soon as the plant was ready to come online, they had people who are actually familiar with that plant. Unfortunately, for the U.S., that wasn't necessarily going to be something that happens anytime soon. But China, for example, does have multiple AP1000 designed plants, and they use them. They use the simulators for those. It actually allows the staff to train on this worst case scenario accident, this loss of coolant accident. It can be modeled for any of the reactor plants that exist in the commercial or military industries. This is hugely important for many reasons. The most impressive thing about it is this is a graph of the 1950s through about 2007 of significant events in nuclear power. And you can see as the industry's improved and grown, so too has the training in the industry. And in the paper that this came from, they discussed specifically how this was a major contribution of this improvement was through the use of simulators. Simulation can be used well beyond just training operators. One of the things that it's used most commonly for is training maintenance personnel. For example, you have to enter the reactor room, you have to perform maintenance on a certain component in there. This maintenance has to be done in a timely fashion to minimize exposure, which is always obviously a goal of the nuclear industry. What you can actually do is you can full-scale three-dimensional model and simulate the whole process from entering the reactor room itself to disassembling the component, making the necessary repairs or maintenance, and then subsequently reassembling it and leaving. This can be performed multiple times in advance of the actual maintenance being performed, and it's actually been proven that this is reducing the amount of time that people are spending performing these difficult, complex maintenance items. Another thing is core modeling has continued to dramatically develop. In the discussion of loss of coolant accidents, one of the major sticking points is that they still can't in real time train a student on the full effects of a loss of coolant accident. What they can actually do, and the reason I'm hesitant with these words, is they can actually model a full-scale loss of coolant accident. However, it still cannot run in real time, even with the current requirement, or even with the current computer capabilities, excuse me. you still can't actually have the intense amount of um, it's actually statistical analysis through Monte Carlo modeling. Um, they still can't perform that in a manner that it can actually take an input from an operator and in real time tell them what's going to happen. However, they can now very accurately model what is going to happen. So, for example, something like Fukushima, they can go back and pretty well estimate what damage has occurred. This also means that they can take a new reactor design and use the engineering data from that reactor and estimate worst case scenario on a loss of coolant accident, what would happen, and get incredibly accurate results. The reason why it's agreed upon now that students can be trained on loss of coolant accidents, though, is that for all intents and purposes, the simulation is close enough. And actually, they can get the point across of what's going to happen, especially with very broad thermodynamic effects. There's also an added benefit of the fact that it can be used for procedural refinement. The simulators provide the opportunity for, like I said earlier, some improved maintenance abilities, but it also can allow them to improve actual plant performance characteristics. In a lot of ways, especially in the commercial industry, the time spent in between either shutdown or startup is time that's costing money. The faster and more efficient they can get these procedures completed, the more quickly they're producing power, the more quickly they're maintaining their capital. So simulators have proven a massive benefit in this aspect. I'd like to thank you all for taking the time to view my presentation. I hope you have a little more understanding and respect of what it takes to be a trainee and work with a simulated nuclear plant environment, and what it takes to actually certify a nuclear power plant. I can provide you any references upon request, and also if you'd like a copy of my slides, feel free to contact me. Thank you, and I appreciate your time.